uh 2, 4, 1, 5, 3, right? Then one way you can do it with the fenwick tree is you just go from right to left, right? And then for each element you see, you want to calculate how many elements to its right are smaller than it. So basically, for each element you're calculating, how many elements have I seen before that are smaller than me, right? Yeah, so in the fenwick tree, we can store at these indices, the frequencies, right? So 0, 0, 0, 0, 0. Yeah, so yeah, so when we're at 3, we haven't seen anything before from 1 to 2, so that just adds plus 0 to the count. And then we mark this as 1. And then when we're at 5, um, we can do a range sum here, and that corresponds to we've seen 3 before, right? So that adds plus 1 to the inversion count. Uh, yeah. And then when we're at the 1, um, like there's nothing that's less than 1, so we just add plus 0, and we make this a 1. And then when we're at the 4, we can take this range sum, and this is 2. Yeah, that checks out with two things being less than 4. And then we mark this as 1. And then when we add the 2, we do this range sum, and that's plus 1, right? So there's 4 inversions. Right. Yeah, that's like checks out with this, and this, right? Yeah, that's a brief tutorial on how to calculate inversions. Um, sorry. Yeah, and yeah, this problem's asking you to do it for all the cyclic shifts. But yeah, yeah, there's like an observation you can make. If you're moving x to the left, then the change in the number of inversions is going to delete a bunch of old inversions. So it's going to be minus and minus x, and then plus, uh, so, and then you add the things that are less than x, so plus x minus 1, right? Yeah. So this is how the number of inversions changes. Just, yeah, you can just calculate an O of 1. You don't need any fancy data structures or anything like that, right? Yeah, so that's how you calculate the number of inversions over all the cyclic shifts. I think this might have been the easier part for me, but yeah, you also need to calculate f of the cyclic shift, right? Because you're trying to count the number of cyclic shifts where f of q is greater than equal to inversions q, right? So it's sufficient to actually it's good enough for us to like calculate f of q over all the cyclic shifts q, right? Yeah. And notice here we have this thing of the form pi minus I. So I like if this is I and this is pi, personally for me it was like kind of hard to like directly interpret like what it means to actually like take the subtract these two. But one thing you can observe, since it's a permutation, right? So permutation has cycles, right? It's gonna look something like this. Yeah, and this is I and this is pi, right? Um, we can instead uh like write it as a sum. It's going to be the same thing, but if you consider the inverse permutation, so pi inverse, uh yeah, that works. Yeah, minus I, right? Basically here you're just reversing the order of the cycle, and that shouldn't change any of the absolute values. So if you take a sum over all indices I of the inverse of the permutation minus I, then yeah, so personally for me, I found this to be like a much more intuitive sum to consider, right? Um, yeah, so yeah, I'll just give an example of like why this inverse might make things easier to visualize, right? So let's just say these are the indices. Yeah, and then yeah, so this is just like 1, 2, 3, 4, 5. Yeah, 1, 2, 3, 4, 5. And then this is the permutation. So this is uh yeah, 5, 2, 3, 1, 4, right? So how you can visualize this like pi inverse minus I is you just look at like the first position here and then find the distance to the one over here, right? And here like this contributes 3 to the sum, right? And then you can also look at other pairs, right? So this 5 over here with this index 5 over here. this contribution is equal to 4, right? So the goal is to like maintain f of q, like the sum of uh, all these gaps as we do all these cyclic shifts, right? So one thing we can notice is like, let's say we shift this once, right? Yeah, that's fine. Yeah. Let's say we shift this once to the right, then it'll look like 4, 5, 2, 3, 1, right? So like initially the 1 contributed 3, but now the contribution of the 1 increased to 4, right? So the contribution equals 4, right? And then initially the 5 contributed 4, but now the contribution decreases to 3, right? So like something you can notice is like um, I guess the endpoint is like a special case you need to handle. But for many of the things, as you shift to the right, the contribution is either going to increase by 1 or decrease by 1, right? Um, yeah, so if the value is to the left of the corresponding index, then the contribution is going to decrease by 1, right? And then if the value is to the right of the corresponding index, then when you shift it, the contribution is going to increase by 1, right? Yeah, so it's enough to like simulate the shifts and maintain a few things. So I'll just summarize like how you can do this, right? So you can simulate the shifts, um, and then you can maintain like the sum of all the contributions, basically the sum of all of these terms of this form. So maintain the sum, and then maintain the number of things that are greater than or equal to the index. For example, like this one over here is to the right of index one, right? Um, and then maintain the number of things that are less than index, right? Um, and basically, like if the value is at a position that's greater than or equal to index, then this will contribute plus, like a positive amount when we shift. And then the things that are to the left of the index, this will contribute a negative amount. Right? Yeah. Any questions? I'll summarize this. Yeah. So this problem is basically asking us to calculate the sum for all the permutations. Yeah. So we're just rewriting the sum like this because personally for me it was easier to visualize. And then you can think of inverse minus the index to actually be the distance between the occurrence of that value and the index. And as you shift the permutation to the right, the contribution of each value is either going to increase by 1 or decrease by 1. And you need to be a bit careful to handle things like the boundary where this 4 jumps over here, right? But it's enough to maintain the sum, and then the number of things that are at a position greater than or equal to index, and then the number of things at a position less than the index, right? Yeah, so when you're actually maintaining this, this only changes O of n times, right? Example of when it changes is, let's say the index, so these are the indices. Let's just say index x is over here, and then this is the current shift. Um, X moved from here to here, right? Initially, X was at a position less than index X, and now it's at a position greater than equal to index X, right? Yeah, okay. Yeah, that's how you do this problem. Any questions? Okay, wait, give me one sec. Um, yeah, I'll just briefly like screen share my implementation. I mean, there's nothing that much new to sh show, but basically, yeah, you can keep track of the number of things that are less, and then the number of things that are greater than or equal to. Yeah, and then this is like the initial contribution, right? And then cur F is basically like the sum of all the terms. And as you shift things, yeah, uh, yeah. So I think yeah, I also have to handle the case where I move something from the rightmost part of the array to the left of the array. Um, but yeah, basically, if something's at a position that's greater than or equal to, then it's going to contribute a positive amount. And then if it's at a position that's less than the index, then it's contribute a negative amount, right? Yeah. Okay. Let me switch my screen share back. Okay. Cool. I'll move on to problem two. Oops. Okay. Yeah, that was this problem. Okay.